Here's an example of a boundary value problem where we use Green's theorem. We have a differential equation, and then our initial conditions is not actually an initial conditions, they're boundary conditions. We have a different x for each of these conditions, and they're set equal to 0. So given this type of boundary value problem, your solution would be one particular solution that is obtained by taking the integral of Green's theorem from the first boundary to the second boundary. And then not Green's theorem but Green's function, and Green's function is split up into two pieces where it's a boundary from a to x and then x to b. So here are the steps that we need to take for the for finding the particular solution. We're going to need to find the fundamental solutions of the homogeneous differential equation, and then we're going to identify those functions as y1 and y2, and one of them will satisfy one boundary condition, the other one should satisfy the other boundary condition. And so that's how we're going to decide which one is y1 and which one is y2, and then we'll use Green's function to solve for the rest. Alright, so what we're going to need to do to begin with is, let's say we need to find out this the solution, or the fundamental solution, which is essentially looking at the solution of this thing equal to 0. So if you remember how to do that, we need to identify the auxiliary equations. And the auxiliary equation for this is going to be this is a second order linear constant coefficients. So our auxiliary equation, we're going to assume that our solution is e to the x, or e to the m times x, and then after we do some work we'll see that the auxiliary equation is this. And so I think this is kind of difficult to factor, so we may have to use a quadratic equation, so that m is going to equal to m is going to equal to minus b, so that's -2 minus -2, and then plus or minus the square root of b squared, so that's 2 squared minus 4 ac. A is 1 and C is 2. Let's put this inside of the square root here. Divided by 2a. So we essentially have 2 over 2 plus or minus, and then we have the square root. Let's see if we can simplify this. This is a 4, and C was equal to 2. So if C was equal to 2, this is 8, and then that really just becomes a -4 inside of the square root. So the 4 inside of the square root will give you a 2. 2 over 2 will give you a 1, and then the fact that it's negative means we're going to have imaginary numbers. So we have complex conjugates for our solutions. That means our y, the fundamental solutions, are going to be it's going to be the set y, I'll just not say y, but it'll be e to the 1 times x. The real part over here is 1, so e is going to have a power 1 times x times cosine of x. 1 times x again, that's the imaginary part. And then the other one is e to the 1 times x again times sine of x. So those are our fundamental solutions, and instead of assigning one of these to be the x and then the other one, or assigning one of them to be y1 and the other one to be y2, we need to identify which one satisfies what. So if we take a look at this, the first initial condition is at 0, so y at 0 is equal to, let's take our first function, e to the 0 times cosine of 0. So that's equal to 1. And unfortunately, that does not equal to 0 as what we want in our fundamental solution or in our boundary. So let's try the second one, and that would be e to the x sine x. So y of 0 is equal to e to the 0 times sine of 0, and that is in fact equal to 0. So that is the sign that says that we should use y sub 1, our first one, to equal to e to the x times sine of x. And just to verify, we should check that. So let's take a look at this and let's say, okay, that didn't work out for us, so let's cross it out. And then this does work out for us, so that's a good check, and then that means that's how we got our y1. Now to check for y2, let's put pi over 2 into the other function. So since we have already used x sine x, let's use e to the x sine x. Let's use e to the x cosine x. So we'll put pi over 2 in there. And that's e raised to the pi over 2 times cosine pi over 2. Oops, let's get that pi looking nice here. And maybe put this in parentheses just so it doesn't look too messy. And this is in fact equal to 0, which is going to be our sign that y sub 2 should equal to e to the x cosine x. Okay, so now we've identified which one is y1 and which one is y2. So now we need to make up Green's function, which means we need to get the Wronskian. So let's get the Wronskian. W so W is going to equal to a 2 by 2 matrix that has y1 first, so that's e to the x times sine x, and then it has y2 in the next slot over here. But we still need to find derivatives, so the derivative e to the x sine x, the derivative of the first is e to the x. times the second is sine x plus the first, e to the x times the derivative of the second cosine x. Similarly over here, e to the x cosine x plus e to the x negative sine x. So let me just put a negative sine x there. And so we want to get the determinant of this. So we have e to the 2x sine x cosine x. See, this might take a little while here. So this is equal to e to the 2x sine x, let's put that in parentheses, sine x cosine x minus e to the 2x, and then we have sine squared of x. So that's the first part, and then we have minus e to the 2x, and then we have another one that's sine x and cosine x. And then minus and then a plus, so that's another minus. And we have e to the 2x, and then we have cosine squared x. Now we have this term over here, and whoops, that underlined the whole thing. Let's see, we can color coordinate this. We have this term over here and this term over here with a negative, so they would cancel each other out. These are both negative, which means we're essentially adding the sine and the cosine with a negative in front. So I think this just turned out to be e to the 2x times negative e to the 2x. Let's put a negative in front of that. Times sine squared and cosine squared. So I'm just going to put 1. Actually, we don't need to put that there. Let's just say that that's our Wronskian. So that's our Wronskian, and then we're going to replace the x with a t according to the formula. And then we got our y1 and y2 identified. So let's set up our equation for the particular solution. So y sub p is going to equal to, this is going to equal to an integral from a to b of this thing, but we're going to integrate from a to x with the first function. Okay, so let's get that set up. We're going to need an integral sign. We're going to go from a to x for this one. That's your t values go for a to x. And then this is going to be a fraction that will include y1 of t. And y1, remember, is the sign, the one with the sign. So this is e to the t times sine of t. So that's the first part, and then we have y2 of x, and so the y2 of x is e to the x times cosine x divided by the Wronskian as a function of t, and the Wronskian is a negative. And then this gets multiplied by f of t. We didn't identify f of t, but f of t is over here. That's e to the t. So let's multiply this by e to the t. Now we cancel one of the e to t's over here. Well, we'll work that out later. Okay, so that's the first part. And the second part, we want to add on another integral, but this time the integral is going to go from x to b. So this is the next integral going from x to b. This is going to be another fraction of an integral, and we have y1, but this time y1 should be in x. And then we're going to multiply it by y2 as a function of t, so that's e to the t times cosine of t. The same Wronskian, and then the same f of t that's included before we put on the dt. Okay. So this is our problem. It comes down to this. Oh, a and b. We know what a and b are. So let's put that in. A is equal to 0, and b is equal to pi over 2. Okay. All right. So now let's just focus on this integral. Let's do it. Well, I was going to say do it one by one, but let's do it all at the same time. Let's take out anything that doesn't have a t in it. So that goes outside of the integral. Let's cancel out 1 and 2 of these. So the e to the t makes this an e to the t, and then the e to the t makes that totally disappear. So we have a negative sign in front. I can get rid of this, and then we can get rid of this as well. Okay, let's actually just get rid of it. So we really just have a sine t dt inside of the integral here, so let's just replace that with sine t dt. So that should be an easy integral, I hope. The same business over here. We have an e to the x sine x. Let's go ahead and take that outside of the integral because it's constant with respect to t. And then we have an e to the t, an e to the t, that's e to the 2t in the numerator, e to the 2t in the denominator, with a negative. So let's change this into a negative. That gets rid of this negative. And then canceling out those e to the t's will leave us with just a cosine of t. All right, so looking good so far. Let's do the actual integral here. So the integral goes sine, the antiderivative of sine is negative cosine. And we are going to take this from 0 to x. So that'd be negative cosine x, and then cosine 0 I think is 1. Okay, we'll do that in a minute. Same business over here. The antiderivative cosine is sine of t, and then we will evaluate this from x to pi over 2. All right, let's continue on. So this thing, after being evaluated, will give us cosine x, negative cosine x. Let's be careful with negative signs. And then we have a minus, and then another minus. Cosine of 0 is 1. So that's the first integral. And second integral, how's this one going to look like? This one's going to look like the sine of pi over 2 pi over 2 minus the lower limit is x, so that's a sine of x. Okay. Oh wait, sine pi over 2. What's sine of pi over 2? Sine pi over 2 I think is 1, so we can replace that with 1. Alright, how's this looking now? Let's see. Let's distribute this. Negative and a negative becomes a positive, and then there's 2 cosine x's. So after distributing that first one, this becomes e to the x cosine squared x, and then that's positive. This is a positive, but then this gets negative distributed times 1 is just going to make this into a negative. So we distributed this term through, and that's what we got simplified. Now let's distribute this negative here, and so multiplied times 1, we just get 1. So that's the first term. And then next we get a negative times a negative, which is a positive. And then we have e to the x sine x times sine x, so that makes 2 sines. So we can actually take this out of the parentheses if we want. Let's do that. Oops. Let's try it again. Take it out of the parentheses. There you go. All right. So we have an e to the x cosine squared x, and then another e to the x sine squared x. So that looks like an e to the x that's ready to come out. So I think from here we got y sub p is equal to e to the x that came out with a cosine squared and the sine squared, plus these other 2 terms. And so I think this should be your final answer. So that's it. This is your solution to that differential equation up there, to this differential equation. Okay, we can check by finding the derivative twice and plugging it in here, make sure we get e to the x. And we can also check by putting 0 and pi over 2 in to make sure that we get the appropriate 0 and the pi over 2. Okay, so I hope that helps, and good luck with your homework.